Greetings, welcome to Lab 6 Part 2. We're still working on inference from numerical data. So we're going to do this time is we're going to take a couple of problems from the textbook and show you how to go about using R with summary data from textbook problems. It's fairly common when you're working with textbooks, at least, that you're going to get just summary data. In the real world, that's not likely at all. In the real world, you're going to get the raw data, the actual data. And the discussion question for this week is going to ask you to work a problem that has some real data in it, and give you some time to flex your R muscle, so to speak. Okay, so let's go take a look. We'll go into RStudio. Let's go take a look at the first question we're going to work on here. Is going to be exercise 5.2. The change in the textbook in the reading for the previous edition, the second edition versus the third edition, is eliminating the material on using the Z distribution versus the T distribution, because in the real world everybody does tests of hypotheses with means with one or two means using the T distribution. If you have more than two means, then you have to use a technique called ANOVA, which we'll talk about in the next module, not in this one. Okay, so anyway, let's get going on 5.2 here. So high school and beyond, part 1. National Center for Educational Statistics conducts a survey of high school seniors collecting test data on reading, writing, and several other subjects. Here we examine a simple random sample of 200 students from the survey, side-by-side box plots of reading and writing scores, as well as a histogram of the differences in scores are shown below. Well, they're actually shown over here on the whiteboard, so let's go back over to that. So if we go over here into the whiteboard, there's the differences in scores, that's the histogram, and those are the side-by-side comparative box plots. So a couple of things to note right away that we see is that the differences, remember that this is each student here is got a corresponding reading and writing score. And what this histogram is it's the data set that is the difference of their reading and their writing. So in other words, if you had student A and they had, let's say, just make up a number, let's say they had a 40 on their reading and they had 32 on their writing, then their difference for student A would be an 8, okay? And then so forth and so on. And so we did that for all of our 200 students that we would go through. And so the numbers that are being plotted over here, this axis right here is the axis of these differences right here. So contrast that over here, we're seeing the actual scores or box plots for each of the scores. So this is every one of the students' reading scores and every one of the students' writing scores done by side-by-side comparative box plots. And what else we see is that these differences, the differences in their reading and their writing scores, appears to have, roughly a bell-shaped unimodal distribution to it, which is going to come in handy here in just a moment. Okay, so let's go back and see if there are any questions we can answer based upon our little discussion so far. So back into RStudio, and it says, is there a clear difference in the average reading and writing scores? Well, I'm assuming they want us to base that on the information that's given here. And not really. I mean, if you look at the reading and the writing scores in terms of their box plots, there's a slight increase in the writing score over the reading score, but this distance between here to here, between the medians, which we're assuming are going to be roughly representative of the means since these distributions don't look horribly skewed. So remember, the mean and the median are about the same in a symmetric distribution. So even those black lines represent the medians, they're probably not too far from the means. And so that distance there is relatively small. So the difference between the reading and the writing scores does not appear to be significantly different. And if you take a look over here in the histogram, that's kind of bore out by the fact that notice that it seems to be centered around 0, and that overall the average difference between reading and writing appears to be approximately 0. Okay, so let's go back over to RStudio for a moment here. And let's go ahead and type in our answer here. So what would we say? Is there a clear difference in the average reading and writing scores? And our answer would be no. There appears to be little difference in the medians. So again, we know we're talking about means here, but we can use the medians as not too far from the mark, so to speak, when we're working with symmetric distributions and talking about the mean. So are the reading and writing scores of each student independent of each other? Well, hopefully, if you're watching this, you finished your reading of the textbook and you know how to determine whether something is independent or dependent, or paired is what we usually say. And in this case, no, they are not independent. No, these are paired data. And the reason we know they're paired data is because each student has an ordered pair assigned to them. So each student had a reading score, each student had a writing score. So these are paired data, like before after data, or two measurements on a single subject is a really good way of thinking about paired data. They're not independent of each other. Now, if we wanted to look at, say, writing scores for all the girls in the class and writing scores for all the boys in the class, those would be independent of each other. They're not matched. They're not paired to each other, okay? So no, these are paired data, not independent. Okay, hopefully that makes sense. So it says create hypotheses appropriate for the following research question. Is there an evident difference in the average scores of students in the reading and writing exam? Okay, so let's go back over for just a second before we do that. Let's take a look at our drawing here and notice that our histogram is based on reading minus writing. So in other words, what we're looking for here is the null hypotheses is going to be something of the nature that we're looking for is going to be what? HO is that the mean for the reading minus the mean for the writing is going to be equal to 0. In other words, there's no difference is what this is saying. There's no difference between the two scores with respect to their averages. So the null hypothesis would say no difference. Clean that up just a smidge there. Give me just a sec. So no difference means, if you think about it back at our previous work with hypotheses, is that no difference means that's the skeptical point of view. They're skeptical that there's any relationship between these two scores. So what would the alternate say? Well, would the alternate say, well, but of course there is a relationship between these two scores. In other words, one of them is going to be different than the other one, which means that the mean for the reading minus the mean for the writing would not be equal to 0. So that's how we would write our null and our alternate hypotheses here. Okay, so how are we going to do that back over here in our RMD and our Markdown file? Now, this is up to you. You can just write mu diff if you want equals to 0, or mu diff not equal to 0. You can do that in English. So if you don't want to do any LaTeX here, you can just say HO mu diff equals 0 versus HA mu diff not equal to 0. But the problem is when you go to put that in HTML, it's going to look ugly, okay? So you're welcome to do that if you want to, and I will accept it, no problem. But for you folks who'd like to see how to make that pretty, of course, we can use a little bit of LaTeX in here to help out here, right? So you can go $, and you can go H subscript, you do an underscore for a subscript O, colon, and now what do we want to do? Well, we want to do mu, so I'm going to go /mu, or excuse me, / mu, and then do an underscore, and let's see, what did we say again? Sorry, I have a brain of very short mental capacity here. Reading, okay, so reading is going to be our first one. So, and then put an R, and then come over here, and then do a subtract, whoop, not bad, get where I need it to be, and then subtract, and then a / mu underscore writing is equal to 0, and then close that off, double space, return, and then let's save ourselves having to type that whole thing again by just copying that and pasting it down here, and we're going to change that equal sign with a / for any for not equals, all right? So let me go ahead and knit that just to see what that's going to look like. Make sure I got my HTML and my LaTeX all bundled together nicely. Yeah, see how nice that looks when you do it that way? Okay, so like I said, totally up to you, but I mean that looks pretty styling. All right, so probably worth taking a minute or two to learn just a wee bit of LaTeX, not a lot of it. You don't need to learn a lot of LaTeX to be able to make math look pretty in an HTML document. Okay, cool. So that takes care of the hypotheses. So check the conditions required to complete this test, okay? So what do we know about checking the conditions for this test? Well, first one, and we've already actually discussed this in the opening part of the problem here, is does the mean of the differences look normal, okay? And so the distribution, as best as we can tell, the distribution of mean differences appears to be normal, which, since this is actually a really large sample size, we could really relax that constraint. And the data is independent. Now, how do we know the independence here? Well, we know a couple things. We know that it's a lot more students than just 200, even though they've got 200 students going on in here, and it's a simple random sample, okay? As long as you think about it, the main thing is what they're trying to get you around to doing is thinking about stuff without just blindly using these tests and not thinking about did you meet the conditions or not. If that distribution differences was horribly skewed to the left or the right, then we may not want to use this technique. That's the main thing. Okay, so average observed difference of the scores is negative 0.545, and the standard deviation of the differences is 8.887 points. Do these data provide convincing evidence of a difference between the average scores on the two means? Okay, so what they're really doing is leading us through, step by step, trying to get us to do a hypothesis test here. And so we need to go in now and calculate our test statistic and our p-value, okay? And we're going to go ahead and, even though they didn't ask us to do that, we're going to say we're going to test at the 5% level. So we'll start off our sentence here saying we will test at the 5% level, because basically what we're doing is we're telling everybody what our decision rule is. Okay, so we're using the 5% level of significance, and now we want to calculate the p-value and our test statistics. We're going to do that by inserting a chunk. We're going to let R do the work for us now. So how are we going to do the calculation here? Well, let's see. We know our t-obs, so t.obs for t observed is going to be equal to, and remember, it's just x minus mu over sigma. That same formula I told you of all the things you got to memorize in the class, that's the only one. It's going to be negative 0.545. That was the mean difference, okay? So that's our x bar difference, if you want to think about it, minus the mean of the null. Well, the null said the difference was 0, didn't it, right? And then that divided by the standard error. Well, the standard error is going to be the standard deviation divided by the square root of the sample size. So let's put that in parentheses. Standard deviation was 8.887. And divide that by SQRT. The sample size here was 200. Okay, so that's our observed test statistic. And now to get our p-value, well, let's see. Let's go draw a picture of this. I can probably do it in my head, but I think it's really a good idea to draw a picture. So let's come over here and see how we would actually draw the picture. So let's get a blank piece here. Okay, so now remember that when we're doing a hypothesis test for the means, from this point forward, we're not going to be working in n by 0 by 1. We're going to be working in the t distribution. And so that point right there, 0, is where the center is at, always in all t distributions. But every t distribution is determined by its degrees of freedom. And we know the degrees of freedom is equal to n minus 1. So in that case, our case, that's going to be 200 minus 1, which is equal to 199. And to be perfectly honest with you, that if I'd used the standard normal of 0 by 1 with this large of a sample size, I would have got exactly the same results. Because as we stated earlier, the t distribution basically for n greater than 30 becomes pretty much the z distribution. But then you start getting into the hassle of when do I use t and when do I not. The reality is if you just use t all the time, you know you got it right. And that's the reason we do things this way. Okay, now we came up with a t observed. Let's go take a look and see what our t observed came back out to be. We can actually get R to give that to us. So let's go ahead and let's execute this line right here. Let's run that. Let's come down here and ask R to echo that for us by just typing in a t obs. And it's negative 0.867. Okay, so let's go plot that t observed value onto our graph. Okay, so that's going to be roughly right about there, negative 8.8, excuse me, not negative 8. Oh my gosh, that'd be crazy way out there if I was thinking like that. So negative 0.8. Let's see, let's get some of the more digits here. 67, that's going to be plenty. So negative 0.867. And we want to find out what is the corresponding area in this tail down here. This region down here will give us half of our p-value. Now remember, we're doing a two-tailed test here. We've got a not equals. And since we're doing a two-tailed test, if you just think about t is very much like the standard normal is symmetric, then 0.867 is going to give us the other half of it. In other words, this region up here is also part of our p-value. Those two red regions together give us the p-value. So a good way of thinking about it is that if I find out what the probability of t being less than negative 0.867 and I multiply that by 2, in other words, I double that, that's going to be equal to my p-value. All right, so how do I do that in R? Well, in R we use the pt command, right? So that's going to be 2 times pt, probability of t, and then I got to give it the endpoint, which is negative 0.867, and then the degrees of freedom, which is 199. Okay, and I double that, and that's going to give me back my corresponding p-value. So let's go ahead and get into RStudio, and let's put that in our chunk. So I'm not going to actually I'm not going to type the number in. I'm just going to use my t-obs because I already did that. In other words, we know the t-obs is negative 0.867274, right? That's what's stored in there, so we'll just use that. So 2 times pt, and then t observed. Put the right parenthesis, actually the left parenthesis in there, and put in t dot obs. There we go. And then put in 199 in there. All right, cool. Let's go ahead and run that. Make sure I got that in there. And then there's our p-value. It looks like our p-value is 0.3868, rather large p-value, okay? So let's come down here, and they ask us to they're asking pretty much to do most of the hypothesis tests in this question. So we gave them our 5% level, we calculated our test statistic and our p-value, and now we need to make our decision. So we would fail to reject the null hypothesis. Why would we fail to reject the null hypothesis? And that's because the p-value is much greater than 5%. Okay, so what does that mean in context? What are we saying here? There appears to be no difference in the mean reading and writing scores. Okay, cool. All right, so what type of error might have been made? Explain what this error means in context of the application, okay? Well, let's see, what did we do? We rejected the null hypotheses. Excuse me, we failed to reject the null hypotheses. Sorry, I said that wrong. We failed to reject the null hypotheses, and thereby you can think of what we did was we rejected the alternate hypotheses. So a type 2 error could have happened here. In other words, we could have falsely failed to reject. I mean, so many negatives. I'm sorry. We could have falsely failed to reject the null hypotheses. See, I really like saying we could have mistakenly rejected the alternate hypotheses. I think that this makes a heck of a lot more sense, which is a type 2 error is we rejected the alternate when it was true. In other words, we could have said what? We need to say this in context, right? We could have said that there is no difference. So we infer there is no difference in reading and writing scores when there might have been. Now, that doesn't mean we made that mistake. In fact, we are pretty confident that we did not. That was the whole reason we set up our high decision rule. We said, hey, we're willing to take a risk of up to 5% of falsely rejecting the null hypotheses, but no bigger than that, okay? And so we would have to accept a probability of falsely rejecting the null hypothesis, basically 40% to reject the null hypotheses. So we're pretty confident that we should not reject the null hypotheses here. Okay, so our chances of having made a type 2 error are probably pretty small, all right? So based on the results of this hypothesis test, would you expect a confidence interval for the average difference between the reading and writing scores to include 0? Explain your reasoning. Well, let's think about this for a minute. We've talked about this in our previous work in Chapter 4, that when we do a two-tailed test, and confidence intervals are actually two sides of the same coin. And that if the hypothesized value of the null hypothesis is contained within the confidence interval, then you would fail to reject the null. If that hypothesized value of the null does not fall into the confidence interval, then you would reject the null. Well, in this case, what did we do? We failed to reject. In fact, we failed to reject by a pretty good margin. Our p-value is rather big, so we would expect it to contain 0. Why would we expect it to contain 0 again? Well, because that's the value of the null hypotheses. Okay, cool beans. All right, so we're going to stop this one here, and we're going to come back in just a bit, and we're going to do exercise 5.29. We're going to talk about where we have independent means, not dependent. We just did dependent. Not paired, but independent means, and we'll talk about how we go about doing that.